section 6.3a, vectors. Now, vectors are a very important concept not only for math but also for science. You'll see them a lot in physics. And so we are going to spend some time on this section. In fact, there will be 3 parts for 6.3 rather than the customary 2 or 1. So this is the first of 3 parts. This will also be the longest of the 3 parts. But the reason that I'm splitting this up is because vectors are sometimes hard to get used to at first. So I think this will help you to ease into it. A vector is a quantity with both a magnitude and a direction. For example, a bullet flies through the air at a certain speed and in a particular direction. The speed and direction are the velocity of the bullet. Now, just a little side note, maybe some of you have wondered what is the difference between speed and velocity? You know, are they just synonyms? We often use them as synonyms in normal speech, but technically, speed just represents a number, you know, miles per hour, but it doesn't take into account a direction. Velocity takes into account both the magnitude, which is the speed, and the direction, which particular way that moving object is going. So the velocity is a vector quantity since it has both a magnitude and a direction. Vectors are used to represent velocity, force, tension, and many other quantities. That's why you're going to see vectors in physics. And the math techniques that we're going to use in this section of 6.3 will be useful to you also in physics. A quantity with magnitude and direction is represented by a directed line segment PQ with the initial point P and terminal point Q. The vector V equals segment PQ is a directed line segment of magnitude PQ, and that magnitude PQ, you'll notice, is between 2 sets of parallel lines. This is simply the symbol for magnitude. That's all it is. And I don't know whether you've seen it before or not. Sometimes people think it looks like absolute value, but it's like absolute value with double lines instead of single lines. But by convention, that is simply the symbol for the magnitude of a vector. Two vectors u and v are equal if the line segments representing them are parallel and have the same magnitude. Alright, this brings up an important point about vectors. So let's look at these next 2 vectors. I've got u and I've got v. Now notice that they're in different parts of the screen. But u has the same magnitude as v, and u has the same direction as v. And therefore u and v are considered equal. See, the thing about vectors that's sometimes hard to get used to is it doesn't matter where they are. They could be north, south, east, west, 1,000 miles apart, 2 inches apart. It doesn't matter. All that matters with vectors is magnitude and direction. Magnitude and direction. So when you get to some word problems that use vectors, that's kind of a nice thing because it means that you can sketch any way you want and draw the vectors in any place that's convenient for you, as long as you have the right magnitude and the right direction. Now, one other point before we go on is that vectors can be written in different ways. The most common way is just with a lowercase letter, and U is a common letter that represents vectors, so is V. You'll see other letters. Another common way is this, this symbol here that I'm circling now with the mouse arrow, which is just a directed line segment. And in that case, P and Q represent points. But you'll see vectors represented in both ways. And we're still going to learn a third way in today's lesson, but let's not worry about that yet. Scalar multiplication is the product of a scalar, or a real number, times a vector. For example, the scalar 3 times v results in the vector 3v, 3 times as long and in the same direction as v. So this would be v, and then the red vector is 3v, and as you can see, 3v goes in exactly the same direction, but its magnitude is 3 times as large. So this is scalar multiplication. Scalar multiplication. If you want to think of it, think of like scale models. A scale model is just something, that represents something else much bigger, but it's smaller. It's on a smaller scale, we would say. Like your typical Hot Wheel car, for example, is 1/64th scale. It's 1/64th the size of a real car. So anyway, when you think of, or when you hear scalar multiplication, don't be scared of that term scalar. A scalar is just a number. It's just a coefficient. It's just something that you times a vector by in order to scale it. You're scaling it up or you're scaling it down. The product of -1/2 and v gives a vector half as long as v and in the opposite direction to v. So this is another example of scalar multiplication, but now what we're introducing is the concept of negative. So let's see what -1/2 v looks like. If that's v, the black vector, well then -1/2 v, the red vector, looks like this. You can see that it's going in exactly the opposite direction, and that its magnitude is 1/2 of v. All right, so that's how negatives work with vectors. They just reverse the direction. This is another illustration just to clarify what I just said about positive and negative vectors. You can just observe these different vectors. And first of all, you'll notice that they're all going the same direction because scalar multiplication never affects direction. It only affects magnitude. Now, the effect that scalar multiplication can have on direction is it can simply reverse it. It can simply reverse it. However, the direction's still going to be parallel. It's still going to be parallel. So, for example, let's look at this original v. We've got v has a certain magnitude and direction. Well, 1/2 v has the same direction, half the magnitude. 2v has the same direction, but twice the magnitude of v. Negative v has the same magnitude, but its direction has been reversed, even though it's still parallel. It's a reversed direction. And -3/2 v has 3/2 times the magnitude of v, but it's going in the opposite direction. Now, we're going to talk about some vector operations. The easiest vector operation we've already gone over. It's called scalar multiplication. But what gets, I wouldn't say like really hard. It's nothing to be intimidated by. But what gets a little bit, I guess, tricky at first is vector addition and vector subtraction. So let's just take it one step at a time, and if you pay attention, you'll see that it does make sense, and it's not so bad after all. So we're going to add vectors v and u. V and u. Now, the way to proceed when you're doing vector addition graphically is as follows. Place the initial point of u at the terminal point of v. All right, so if you can think of it this way, I like to think of the initial point as the tail and the terminal point as the head. Well, then you put the tail of one on the head of the other. That's how you set it up. Then you draw the vector with the same initial point as v and the same terminal point as u. All right, and so this, as you can see, is the same as v plus u. V plus u is the same as u plus v because they end up in the same place. They end up in the same place. And so we have this initial point here of u plus v, and it ends up at the terminal point of u. Now, of course, as I said already, you could just as easily write this u plus v. You could just as easily write it as v plus u. Vector addition is completely commutative. It's completely commutative. It doesn't matter. The order doesn't matter there. All right, so that's vector addition. If you think of it this way, you can think of v as going a certain magnitude and direction, and then it's being influenced by u, which is going a certain magnitude and direction. And that influence, right, taking v and u into account and their effect on each other, will give you u plus v. All right, so make sure that you understand that for vector addition, you put the head of one on the tail of the other, and then you just connect from head to tail, the head of one to the tail of the other, and you've got your answer. This is what the sum of two vectors looks like, and I think this will make it a little more clear just to see. Let's look at the left. Now we've got u and we've got v, and you can see they're separated. You know, they're not touching. But the beautiful thing about vectors is that you can draw them anywhere, and they're still equivalent, because all that matters with vectors is magnitude and direction. Now you can see here that this, what I'm tracing now with the mouse arrow, this gray vector, is u, and you can see that it has the same magnitude and direction as u does over here on the left part of the screen. It's just that we've been, we're just drawing it with a different color. And this v here has the same magnitude as this gray v up here, this gray vector v. It's just that we've drawn it in a different place. It's convenient for us to put v lined up so that the tail of v touches the head of u. I'll say that again. Look over here at the right, and you'll see that the tail, or initial point, of v touches the head, or terminal point, of u. Now when we do that, we can clearly see where u plus v ends up. U plus v ends up as connecting the tail of u to the head of v. And that's our u plus v. Now, just to make sure we understand then, qualitatively, okay, we're not talking quantitatively yet about specific numbers, but let's just understand vector addition qualitatively. Okay, so we can see that, looking here on the right, we see that u has a certain magnitude and direction, and v has a certain magnitude and direction, but they influence each other. And so u plus v has a direction that's similar to both u and v, but it's a little different because, as you can see, v kind of pushes u over. And we can also see that u has a certain magnitude and so does v, and so they reinforce each other and give us a u plus v vector that has a bigger magnitude than either one of u and v. So qualitatively, that's what vector addition is. It's just adding magnitudes and directions to get a final or resultant magnitude and direction in your vector sum. U plus v is your vector sum. Let's look now at vector subtraction. To subtract vectors u and v, place the initial point of v at the initial point of u. Okay, so now we're putting the two tails together. Draw the vector u minus v from the terminal point of v to the terminal point of u. All right, now the thing about this is the thing about vector subtraction, is that it's a little less intuitive than vector addition, because vector addition is, just putting heads and tails together and lining up. And actually, if you look at it graphically, vector addition just makes sense, But the trouble with vector subtraction is when you look at it, it's not exactly intuitive of why you have to, draw u minus v with its tail at the head of v and its head at the head of u. All right, so the best way to understand this is by looking at vector subtraction in a different way. And we're going to do that on the next screen. But first, make sure you have all of this copied down correctly. All right, so here's a way to visualize the difference of two vectors. Let's look at these two vectors written or drawn in gray. We've got vector u and we have vector v. Now, if you look at the bottom of the screen, you'll see, I'm talking about the bottom left portion of the screen, you'll see this little equation that says u minus v equals u plus minus v. All right, well, that's obvious, right? You know that subtraction is just like adding the negative. But the reason it's helpful is because this helps us to visualize what vector subtraction does. All right, let's suppose that we're considering vector subtraction as just the addition of two vectors, but one of those vectors happens to be negative. Well, this is what it would look like. You've got your gray vector u, see that? I'm tracing it now with the mouse arrow. And then you just proceed as you do with vector addition, and you put the tail of one on the head of the other, and just connect them. And notice where you end up. You end up right here at this little part, this little point that I'm tracing with the mouse arrow. This is where u plus minus v ends up. U plus minus v ends up right here. And that's why we can draw this vector u plus minus v, because it simply connects the tail of the first vector to the head of the second vector. It's just like vector addition. But notice that this u plus minus v vector, this u plus minus v vector that we found by adding u and negative v, this is exactly the same as the vector u minus v. The vector u minus v, even though it's being drawn over here for the sake of clarity, you can see that it has the exact same magnitude and the exact same direction, and therefore u minus v is exactly the same as u plus minus v. Okay, so this really is just a way to visualize of why what I showed you on the last screen is true. Okay, when you have u minus v, you just put the initial points together, and then whatever is being subtracted, in this case v, you just connect the head of v to the head of u, and you have your right vector. But what you can always do, of course, is just think of u minus v as u plus minus v, and that will help you to visualize as well. A vector with initial point 0, 0 is in standard position and is represented uniquely by its terminal point u1, u2. All right, so the coordinates u1, u2, u1 would be an x-coordinate, and u2 would be a vertical or a y-coordinate. All right, so let's look at this vector. You got your x-axis, your y-axis, and you have your vector u. And you can see that it's very convenient to put the initial point at 0, 0, because then your x-coordinate for the terminal point represents the horizontal component of vector u, and the y-coordinate of the terminal point, this y-coordinate u2, represents the vertical component of the vector u. And so that's why when you see a vector written this way, this is our third way of writing vectors, the one I mentioned that we get into later. We've seen, the directed line segment way of representing vectors. We've seen the lowercase u or v way of representing, and this this notation of a kind of funny-looking bracket. Think of it as somewhere between a bracket and parentheses. These two diagonal lines that join. Okay, this is a way of representing a vector in component form. And what that means is the first number, in this case u1, represents the horizontal component of the vector. That is, how much of the vector goes horizontally. And the u2, or the second component in component form, represents the vertical component of the vector, or how much the vector goes up vertically. And so when you see these symbols, this kind of strange looking parentheses or bracket, some people, like Star Wars fans, like to think of it as the wings of a TIE fighter. But I don't know if that even means anything to you. But whenever you see these kinds of symbols, just think of it as a component form vector. It's a component form vector. Now, I'm going to explain a little bit more about what we mean by component form. So don't worry about that if you don't understand it yet. But just make sure that you recognize this notation as component form. Now let's see what exactly it means. If V is a vector with initial point P equals P1, P2, and notice these parentheses just indicate that we're talking about an x-coordinate and a y-coordinate, and terminal point Q equals Q1, Q2, where Q1 is an x-coordinate and Q2 is a y-coordinate, then the component form of V is V equals Q1 minus P1, comma Q2 minus P2. And let's look at the graph and see why that's true. All right, let's look at this vector PQ. You can see that the point P has x-coordinate P1 and y-coordinate P2. The coordinate Q has x-coordinate Q1 and y-coordinate Q2. Well, notice that what we really want, since this vector is not written in standard position, standard position would have our initial point at the origin, and here it's clearly not at the origin. But we can figure out what the horizontal component is because we just get the distance, the x distance. And we can clearly see here that Q1, or the x-coordinate of the terminal, minus P1, or the x-coordinate of the initial, gives us the total x distance. And Q2 minus P2 gives us the total y distance. And therefore, we will have the vector in component form. We'll have our horizontal component and our vertical component. Now, also the magnitude. In this case, we can also consider magnitude a length because we're, drawing a vector. Magnitude, of course, isn't always a length. Sometimes it's just in amount of force or an amount of velocity, but it's convenient to visualize it as a length, especially for now. And so the magnitude of V is given to us by the distance formula. Okay, we've been seeing this a lot. We saw it in Chapter 1. You probably saw it a bit last year. We used it a bit in Chapter 4. But these two double lines, of course, represent magnitude. And it's the square root of Q1 minus P1 squared plus Q2 minus P2 squared. And that comes directly from the Pythagorean formula. Okay. And we're just looking at it as a right triangle. Like if you look at where my mouse arrow is now, I'm just tracing out the horizontal distance. In fact, I can just use my little pen here, and we can make a nice little rough right triangle to illustrate this better. Okay, so of course this is not a perfect horizontal line, but you get the idea. Okay, so that would be the horizontal distance, and then this would be the vertical distance. So you can see that it traces out a right triangle, right? And therefore, this vector would be the hypotenuse of the right triangle, and that would be given to us as if we consider this our horizontal component, and so this would be V1, and I'm calling it V1 because if you look over here, my vector is called V, and so V1 would simply represent the horizontal component. Then I could label this as V2, and V2 of course would just be my my vertical component. So I've got V1, V2, and so clearly I can see that the hypotenuse squared is V1 squared plus V2 squared, and that's where this comes from. Since V1 is the same as Q1 minus P1, I write that here. And since V2 is the same as Q2 minus P2, I write that here. And based on the Pythagorean formula, I get the formula for magnitude. All right, now, if you're still a little fuzzy about what a component is, don't worry, because we're gonna be explaining it even more. Remember what I told you, that vectors are hard to get used to in the beginning. That's why we're spending 3 different days on this section. And so don't be surprised if it's a little foreign at first. But as usually happens with math, the more you do things and use certain terms and formulas and see certain graphs, the more you get used to it and the more you understand. All right, but for now the important thing is to write down this formula for magnitude, which really just comes from the Pythagorean formula, and write down this formula for component form of the terminal point, the terminal x-coordinate minus the initial x-coordinate, comma, terminal y-coordinate minus initial y-coordinate. All right, now let's go on to the next screen, and hopefully this will become even more clear. Example, find the component form and magnitude of the vector v with initial point p equals 3, -2, and terminal point q equals -1, 1. So let's write things out, because that'll help us to keep straight what we're trying to find here. If the initial point is p of my vector, this vector v is the same as the vector or directed line segment PQ. We're just calling it v. All right, well then P1's x-coordinate, or the P1 x-coordinate is 3. That's the x-coordinate of point P. And the P2 y-coordinate is -2. That's the y-coordinate of point P. We also see for Q1, Q2, we have -1, 1. So V1, or the horizontal component of V, that's V1, the horizontal component of V. How much of vector V goes horizontal? That would be -1 minus 3, and that's -4. And V2, or the vertical component of the vector V, how much of the vector V is vertical, will be 1 minus -2, and that's 3. Notice we get the 1 from here, that's Q2, and we get the -2 from here, that's P2, and so Q2 minus P2 is 3. Therefore, the component form of V is -4, 3. Now notice we have these funny TIE fighter wings, right? If you want to call them those. These funny TIE fighter wings, when you see that symbol, you should automatically be thinking, oh, that is a vector. And the numbers inside those TIE fighter wings are components. Horizontal first, vertical second. Horizontal first, vertical second. Now let's look at a diagram that I think will help to visualize all of this. All right, if we look at this graph, this is a graphical representation of everything we just did. Let's take it one step at a time. This is my point P. I'm circling it now with the mouse arrow. It's the point 3, -2, and we can graph it right on our Cartesian coordinate system, 3, -2. And then if you look over here, where I'm circling now with the mouse arrow, we have the point -1, 1. That's the point Q. I connect the dots, and I've got my vector. I've got my vector with the arrowhead. And since my initial point is P, then that would be the tail of my vector. And since the terminal point is Q, that's the head of my vector. Now, the reason that I'm putting this illustration here in the slide is because I think it shows pretty clearly what we mean by components. Okay, so let's consider this vector the hypotenuse of a right triangle, and I have dotted lines representing that right triangle. Now, the length of the base of this right triangle is 4, but I'm labeling it -4. I'm labeling it -4 to show that it's going left rather than right. It's going left rather than right. And if I look at this vertical, or this height of the right triangle, I'm labeling it 3 because it goes upwards, not downwards. It goes upwards, not downwards. Now, what this should show you is that even though we're dealing with a diagonal line here, this vector, a diagonal line has a certain amount of it that goes horizontally and a certain amount of it that goes vertically. And if you count up the points on the grid, you'll see that the amount of horizontal in this vector is 4. And I'm putting -4 because it's going left, just to show the direction. And the amount of vertical in this diagonal vector is 3, and you can just count up the different grid boxes here to prove that to yourself. Okay, so that's what we mean by components. That's what we mean by components. The negatives and positives simply tell us whether a component goes up or down or left or right. With vertical components, negative is down and positive is up. With horizontal components, negative is left and positive is right. The magnitude of v, the magnitude of this vector v, is, using the Pythagorean formula, the square root of -4 squared plus 3 squared, and that's root 25, and that is 5. And therefore I can label my vector as having a magnitude of 5. And again, this is helpful just for understanding vectors at first, because you can see this is your common 3, 4, 5 triangle, your 3, 4, 5 right triangle. You saw that in geometry, you probably saw it in algebra 2, so it's nothing new for you. But of course, 5 is bigger than 4 and 5 is bigger than 3, but this diagonal line 5 has a horizontal component of 4 and a vertical component of 3. Two vectors u equals u1, u2, and v equals v1, v2 are equal if and only if u1 equals v1 and u2 equals v2. Alright, here's the whole beauty of the component form. The whole beauty of component form when we're dealing with vectors is that you don't have to graph them. You don't have to worry about the signs or anything. If you just first take care of the horizontal components and then take care of the vertical components, you will get an accurate vector addition or accurate vector subtraction. So, like, for example, if you don't like all that stuff about heads and tails and graphing and drawing your vectors and stuff, well, then the component form is your friend. The component form is your friend. And stay with me and you'll see why. All right, let's look at this example. If you got u equals pq, that's one vector, v equals rs, that's another vector, and w equals tu, directed line segment tu, with points p equals 1, 2, q equals 4, 3, r equals 1, 1, s equals 3, 2, t equals -1, -2, and u equals 1, -1. Determine which of u, v, and w are equal. All right, well, I'm just going to walk you through this, and you'll see why it's true. Okay, so first you calculate the component form for each vector. U, all these numbers, it's simple where it comes from, okay? Remember that u is pq. And so, if you look at point P and point Q right now, you've got 1, 2, and 4, 3. That's PQ. And so, you just look at Q1, which is 4, minus P1, which is 1, and it's 4 minus 1. You look at Q2, which is 3, and P2, which is 2, 3 minus 2, and you get 3, 1. All right, and similar process goes for all of these vectors. Now notice, on purpose, we're not referring to any graph here, because with component forms, if you're consistent about just adding the horizontals first and then adding the verticals next, then you'll always end up with the right component form. And so the component form of u is 3, 1. That means it has a horizontal component of 3 and a vertical component of 1. The component form of v is 2, 1, horizontal 2, vertical 1. And the component form of w is 2, 1, horizontal 2, vertical 1. And clearly we can see just by looking at these component forms, we see that v equals w, same exact component form. But, of course, v is not equal to u and w is not equal to u. Alright, so operations on vectors in the coordinate plane. What we see on this screen is probably going to be the most useful to you, not only for this section, but for the remainder of this section, and even for physics and beyond, because most of what you'll be doing is using component forms. So let's look at these two vectors, u equals u1, u2 in those TIE fighter wings, and v equals v1, v2 in those TIE fighter wings. And let c be a scalar. So the scalar multiplication is just cu, and all you do there is you multiply the horizontal component by c and the vertical component by c, and you've got your scalar multiple. You have your vector that's been scaled So that's easy. It makes it easy to split things up like that. With addition, u plus v is just u1 plus v1, comma u2 plus v2. So notice that if you have a vector u and you have a vector v, you just figure out the component form for those vectors, and then you add. First, you add the two horizontal components, u1 plus v1. Then you add the two vertical components, u2 plus v2, and you will get the correct sum. You'll get the correct sum, no matter what the signs or magnitudes are. Same goes with subtraction. U minus v, it's just horizontal of u1, so horizontal component of u, which is u1, minus the horizontal component of v, which is v1, comma, vertical component of u, which is u2, minus the vertical component of v, which is v2. And you'll always get the right answer. Examples, given vectors u equals 4, 2, and v equals 2, 5, find negative 2u. All right, well that's easy, right? Because negative 2u is just a scalar multiple. It's negative 2 times component form 4, 2, and that's just negative 8, negative 4. And this is what it looks like. Okay, we've got a rough sketch here, and this of course is vector u, which is 4, 2, and the scalar multiple of it, negative 2u. You can see that it goes in exactly the opposite direction, and it has twice the magnitude. But before we even graphed, we were able to get the right component form just by following the rules that were on the last screen. All right, I'd like you to try to sketch this one on your own. U plus v is just, the vector 6, 7. Because you can see we have u, 4, 2, and v, 2, 5. We just add the horizontals, 4 plus 2 is 6. And we add the vertical components, we get 2 plus 5 is 7. And therefore we have the right sum. So pause the video, try to sketch this, and then resume when you have a sketch. You're going to sketch both vectors. And this is what you got. You got 4, 2, that's your u. You got 2, 5, that's your v. You of course can assume that they are in standard position, and that's why the initial points are just 0, 0. And u plus v, we can see, is 6, 7. Now notice that u plus v is going right between these two, but the same rule that we learned at the beginning of this section of the heads and tails, it applies. Notice that if we look at this v here that I'm tracing with the mouse arrow, if we take the tail of this v and put it on the head of u, you'll notice that it ends up in exactly the same point. It ends up in exactly the same point. All right. Now again, this is going to be kind of a rough connect the dots, but I'm going to connect these two dots here. Okay. And you can see that this rough little line that I just drew, it lines up perfectly with v. It's the same direction, same magnitude. It is v. It is v. It's just a different place, place to draw v, but it comes out the same. It still comes out exactly the same. And so we see that whether you add vectors graphically or you add them by the component forms, you're going to get the same sum. All right, finally, u minus v is just this 4, 2 minus 2, 5 equals 2, negative 3. And again, let's see how that works. We've got u, 4, 2. We've got v, 2, 5. Now we're subtracting. And notice that this u minus v, which ends up being 2, negative 3. And you can see why it's 2, negative 3. Horizontal component of 2, vertical component of negative 3. And we get that just by subtracting the horizontal components and then subtracting the vertical components. And notice that it's going to be in exactly the same place as we would have the vector if we did it graphically, right? So doing it graphically now, this would be where u minus v would end up. And notice that this hand-drawn u minus v is the same magnitude and direction as the u minus v down here. It just happens to be drawn in a different place. All right, so the good news for you is that if you keep your components straight and just work with component forms, you'll never go wrong. And so whenever you get a vector, your first step should be just to try to convert it to component form. Here's the classwork. Page 456. Please write these numbers down and see you in class.